All right, ladies and gentlemen, the purpose of today's lecture is to discuss the valence shell electron pair repulsion theory, otherwise known as the VSEPR theory. This lecture should immediately follow your investigation into Lewis dot structures, and the key idea we want you to get out of today's lecture is that you can make predictions about the structure and shape of a molecule based upon the bonding structure you've drawn as a Lewis dot structure. So let's go ahead and get started. That big, huge mouthful of a name here, the valence shell electron pair repulsion theory, is really just a fancy way of saying that electrons repel from one another. Electrons are negatively charged. Negative charges repel other negative charges. And as such, in a molecule, the three-dimensional shape of that molecule should be based upon that repulsive force of the electrons pushing the parts of the molecule as far away from each other as possible to minimize that repulsive force and thereby put the molecule at a state of lower potential energy. As we're going through in order to determine the shape of a molecule, the first thing we want to look at is where those electrons are found around the outside of every central atom. And those regions in space where we find electrons are what we refer to as electron domains. So we're going to go ahead and define an electron domain as being just one place in space where there are electrons, regardless of how many electrons are actually present. That is to say that that region could contain a pair of electrons, a lone pair of electrons. It could contain a single electron by itself. It could contain a bonded pair of electrons, or it can contain multiple bonded pairs of electrons, that is a double or a triple bond. For the purposes of determining molecular geometry, we're going to treat all of those different regions in space where there are electrons as equivalent. That is to say, the domain is not dependent upon what is in it, how many electrons there actually are. All that matters is that there are electrons present in that domain. Now, in order to count those electron domains, all we want to do is look around each central atom. So if you have a look at this molecule we've drawn down at the bottom right here, in this molecule, we have two central atoms. They are both carbon atoms bonded to other atoms around the periphery of the molecule. We're going to go ahead and label these as carbon 1 and carbon 2 on our Lewis dot structure. And in order to determine the geometry around those two carbon atoms, we want to be able to count how many of those domains are actually present around each one of the carbons. That is, how many regions in space do we find the negative charge due to the presence of those electrons. Now, a key idea here is that when we're identifying the electron domains, what we're interested in is the geometry around each central atom, not the geometry of the molecule as a whole. That is to say, in the Lewis dot diagram we're looking at right here for our compound CH3CHO, we're going to describe the geometry around each of those central atoms, carbon 1 and carbon 2, rather than the geometry of the molecule as a whole. So let's go ahead and start by just taking a look at the number of electron domains around each of our central carbon atoms. Around carbon 1, you'll notice that there are 4 regions in space where we find electrons. Those are the bonded pairs of electrons that exist between the 3 carbon-hydrogen bonds and the 1 carbon-to-carbon bond. So we would say around carbon 1, there are 4 electron domains. That is, there are 4 regions in space where we find those electrons, all of which happen to contain singly bonded pairs. Having looked now at carbon 2, we find that there are in fact now 3 regions in space where we find electrons. We have the carbon-to-carbon bond, which is one region, a carbon-to-hydrogen bond, which is the second region, and now a carbon-to-oxygen double bond, which again counts as just one domain. That is one region in space where we find electrons. So we say carbon 1 is surrounded by 4 electron domains, carbon 2 is surrounded by 3 electron domains. And again, we're interested in describing the electron domains around each central atom, not the sum of the electron domains for the molecule as a whole. Now, in order to assist you in determining the shapes of these molecules, we have given out to you in class a handout, and that handout has 2 distinct sides. On the front side of that handout, you'll see it labeled Table 10.1. The front side of that handout shows you the geometry dependent upon the electron domains around a central atom in which none of the domains are occupied by lone pairs of electrons. That is to say, around the central atom, all of the electron domains contain bonded pairs. Whether they be single bonded or double bonded doesn't matter. What does matter, however, is that there are no lone pairs of electrons occupying any of those domains. On the reverse side of your handout sheet, there is a table labeled Table 10.2. This table gives you the geometries of molecules which do contain lone pairs of electrons occupying at least one of the domains around a central atom. So I would take a moment to just make sure on your own handout on Table 10.1, just in big letters up at the top with a star around it, you label this side as no lone pairs. And on Table 10.2, again up at the very top there, in big letters with a star around it, label this one as lone pairs, so you can figure out which side of this handout you need to be using in order to determine the geometry of your molecules. So with that kind of general framework put in place for determining the number of electron domains, let's see now how we can use our ability to determine electron domains together with your handout in order to determine the shape of a molecule. And in order to do so, I think a good visualization to have here is to kind of imagine those electron domains as representing something kind of along the lines of balloons around a central point. Just like taking a bunch of balloons and pushing them around a central point, the electron domains repel from one another to put themselves into a lowest potential energy configuration, minimizing that repulsive force. And if you can kind of visualize here some balloons, we can kind of see the shapes that the balloons take on in the same sort of fashion, in that the balloons tend to minimize the repulsion between each other by spreading out into three-dimensional space, occupying that space in such a way that minimizes that push between the balloons. So if you take a look at the first set of balloons right here, all of these balloons are attached around a single central point, and around that single central point, you'll notice in the first example here, we have 3 balloons placed around the outside. So if we have a single central point with 3 balloons placed around the outside, you'll notice that the shape those 3 balloons take on is kind of like a triangular shape in which all of the balloons exist in the same plane. And as such, we refer to this geometry of balloon arrangements here as a trigonal planar geometry. That is, they occupy a triangular shape in which all of the balloons exist in a single plane. So again, we call this trigonal planar geometry. And that trigonal planar geometry occurs when you have 3 domains, that is 3 balloons around a single central atom. All of the domains being occupied by atoms. That is, none of the domains are occupied by lone pairs of electrons. Now, if we change our system here and add another balloon, all of a sudden now we've got a total of 4 domains around our single central point. And you notice that changes the shape of our molecule in that we now have one of the balloons up at the top there, but then 3 of the balloons are kind of pointing downwards. And you'll notice that the angle between those balloons is not a 90-degree angle, as you might imagine if you looked at a Lewis dot structure of a molecule showing this geometry, something like, let's say, methane, CH4, a molecule who, when we draw its Lewis dot structure, looks very much like it has 90-degree angles between those atoms. But instead, you take a look there and look at that angle between the balloons, and you'll see that that angle is actually significantly greater than 90 degrees. In fact, as it turns out, it's right around 109.5 degrees for the bond angle. So this arrangement of balloons around a single central point in which there are 4 bonded domains is what we refer to as a tetrahedral arrangement of the electron domains. Tetra meaning 4, and a hedron being side. So the tetrahedral arrangement refers to a 4-sided figure. And looking at the next example here, you can see as we add yet another balloon, again, the shape changes again. Those balloons spread out to occupy 3-dimensional space in such a way that minimizes the repulsive forces between them. If we now have a total of 5 domains around the central point there, you'll notice that 3 of those domains occupy points kind of in a plane And that plane is kind of triangular in shape, so we have 1, 2, and 3 of those domains. And then one of them is up above, and one of them is down below. And you'll notice kind of that the shape that this now makes is kind of like a double pyramid above and below a central triangle. So we call that shape here now a trigonal bipyramidal geometry. That trigonal bipyramidal geometry is the geometry that molecules take when there are 5 electron domains around a single central point. So again, here looking at our balloon diagram here, you'll notice we've got kind of triangular shape, and then we've got the pyramid on the top and the pyramid on the bottom there. So a trigonal bipyramidal geometry. And last but not least, our final domain there, in which we have a total of 6 bonded pairs of electrons around the single central atom there. That is 6 domains. At this point now, you'll see we've got kind of a similar thing going on here, in which we now have a plane, but this time the plane is occupied by 4 balloons in the plane, and then there's one up above. So if again we connected all those points, we'd end up with kind of a pyramid again, but now a 4-sided pyramid, and then the same sort of thing happening down below, as you can imagine here, for another pyramid down below. And you notice as I connect all those vertex points together here, I end up with an 8-sided figure, kind of a 4-sided pyramid above and below. And that 8-sided figure that we generate by connecting those vertex points gives us the name of this particular geometry, which we refer to as octahedral geometry. Octa referring to the number of faces on the figure, not to the number of electron domains. There are 6 electron domains, which together create an 8-sided figure for an octahedron. So you can kind of see here now, looking at our balloons, how the shapes of those balloons are dependent upon how many of them we stick around our central point. And that's the whole idea behind the VSEPR theory, the valence shell electron pair repulsion theory, is that we can predict the geometry of the molecules based upon the repulsion of those electron domains. So let's go ahead and now take this idea and apply it to a couple of problems which we dealt with on problem set 412, which you've just completed for your Lewis dot structures. So take a look with me. Let's go ahead and start by the molecule carbon dioxide CO2. You drew in problem set 412 a Lewis dot structure for carbon dioxide, in which you found there to be a single central carbon atom, and that central carbon atom is bonded to 2 oxygens on either side using double bonds, and then there are lone pairs of electrons to complete the octets on the oxygens around the outside. And what we'd like to do now is, with a valid Lewis dot structure drawn, we'd like to use this now in order to determine the geometry around the central carbon atom. So having a look here, looking at my central carbon atom, I notice that there are in fact only 2 regions in space where there are electron domains. That is 2 places where we find electrons distributed. And as it turns out, each of those domains happens to be occupied by bonded pairs of electrons. But again, whether it's a single bond or double bond does not matter for geometry purposes. All that matters is that that is a region in place where there's negative charge, which will repel other negative charges. So looking at your molecular geometry sheet on table 10.1, you'll notice on that side, for a molecule which has a total of 2 electron domains around the central atom, that it tells you the geometry of this molecule is linear, in which there is a 180-degree bond angle between bonds. And this kind of makes logical sense again if you can imagine the shape that would be taken by a set of 2 balloons around a single central point. The shape of that set of balloons, to minimize the repulsion between the balloons, would be the greatest angle you could possibly put between them, that angle of 180 degrees. So we say that carbon dioxide, the central carbon in carbon dioxide, exhibits linear geometry. Let's take a look now at a second, a little bit more complicated example. Have a look for me, please, at a molecule of sulfur trioxide, that is SO3. So let's go ahead and draw our Lewis dot structure for sulfur trioxide. We have a single central sulfur atom and 3 oxygens around the outside. And the sulfur trioxide molecule which you drew the Lewis dot structure for on your homework set has a double bond between one of the oxygens and the sulfur and single bonds between the other two. And then lone pairs of electrons fill up the octets for the oxygens around the outside. So here's our Lewis dot structure for sulfur trioxide. Let's now go ahead and determine the number of electron domains around our central atom, in this case that central sulfur atom. So looking around the sulfur, I have a total of 3 domains, one of which contains a double bonded pair of electrons, 2 pairs of electrons, and 2 of which contain single bonded pairs of electrons, for a grand total of, again, 3 electron domains. All of those electron domains contain bonded pairs of electrons, and so we're still on the side which has no lone pairs, that is table 10.1. And you'll notice here that on table 10.1, it lists for us here a geometry in which we have 3 electron domains of trigonal planar geometry. Again, that should look very, very familiar, just like the set of 3 balloons spreading out into a plane in a triangle shape. The sulfur trioxide molecule does the exact same thing. And the angle between those we have as a 120-degree bond angle. So there's our first couple of examples here. Let's try one more, a little bit trickier one here. Let's now go ahead and look at a molecule of sulfur dioxide, that is SO2. So looking at the molecule sulfur dioxide, SO2, from your homework set, you drew a Lewis dot structure for this molecule, in which we have a sulfur bonded to 2 oxygens. One of those bonds contains a single bond, one contains a double bond. Then we have a lone pair of electrons on the central sulfur, and then we'll complete the octets for the oxygens with lone pairs around the outside. So here's our Lewis dot diagram for sulfur dioxide. And again, in order to determine that geometry, we're going to do the same thing we've done up until this point, which is to determine the number of electron domains around the central atom. Now in this case, for sulfur, we in fact have 3 domains, one of which contains the bonded pair of electrons between the sulfur and the oxygen. One of those domains contains a double bonded pair of 2 electron pairs between the sulfur and the oxygen. And then the third domain is the lone pair of electrons on the central sulfur atom. So again, we have a total of 3 domains. However, one of those domains is occupied not by a bonded pair, but instead by a lone pair of electrons, which means we need to flip over your molecular geometry sheet onto the opposite side, that is to table 10.2, which you earlier labeled with a label that said lone pairs of electrons. You'll notice on this table, the total number of domains for our molecule is 3 total domains, but of those 3 domains, we have 2 of the domains which contain bonded pairs, and one of the domains which contains a lone pair. So we've got 3 total domains, 2 bonded, and 1 lone. And so looking at your geometry sheet, go ahead and find the geometry for 3 total electron domains, which contain 2 bonded pairs and 1 lone pair of electron. It tells you that the arrangement of the electron pairs, that is the arrangement of the domains for where we find electrons, is still trigonal planar. However, because one of those domains is not occupied by a bonded pair of electrons that is bonded to an atom, the actual shape that the molecule takes on here is what we refer to as bent geometry. So around that central sulfur atom, we say the geometry is bent geometry rather than trigonal planar, as we'd expected if all of them can contain bonded pairs. And the idea behind this is essentially here's what our molecule looks like. We've got sulfur, oxygen, oxygen, and then here's our lone pair of electrons. So here's the actual shape of the molecule. And you'll notice, just like before, the arrangement of the domains is the same trigonal planar shape that we saw before. However, when dealing with electron when dealing not with electron domains, but instead with the molecular geometry, that is the places where we find the actual atoms in the molecule, the actual atoms are lined up in this kind of elbow-shaped pattern, which we refer to as, again, bent geometry, recognizing that there really is no atom up here at the top where the lone pair of electrons is, and therefore does not affect the actual shape of the molecule. So we refer to this as now bent geometry. Let's go ahead now back and look one more time here at an example which we came to earlier on our set of notes, on the very first page of our notes, where we drew for you the diagram of the 2-carbon molecule here. And let's talk now that we've talked about the geometries of some simpler molecules, let's talk about the geometries around this more complicated looking molecule. Please remember here, guys, that even though this thing looks bigger and scarier, that doesn't mean that the geometries around the central atoms are any bigger or scarier than they would be for the smaller molecules we've talked about here. The key idea, again, is that the geometries which we discuss are the arrangements of the domains around the central atoms, not of the molecule as a whole. So for this particular molecule, we're going to label separate geometries for both carbon 1 and carbon 2. So applying our rules, looking at carbon 1, there are a total of 4 domains around carbon 1, all of which contain bonded pairs of electrons. And looking at your sheet on the side of table 10.1, where we have no lone pairs, an electron domain arrangement where we have 4 bonded pairs of electrons gives a geometry around carbon 1 of tetrahedral geometry. And now considering carbon 2 has 3 total electron domains, 2 of which contain single bonds and 1 of which contains a double bond. So around carbon 2, we would say that its geometry is trigonal planar as a position on the molecule where we have a total of 3 domains, all of which contain bonded pairs. So again, the geometries refer to the arrangements of the atoms around each central atom in the molecule, not of the molecule as a whole. So in molecules where you have multiple central atoms, you need to list the geometry of each of those central atoms, not just of the molecule as a whole. So at this point now, we are now able to determine geometries around each central atom in a molecule. The reason why we want to be able to do this is because, as it turns out, the geometry of the molecules that we observe directly relates to their chemical behaviors and physical behaviors which we see in the real world. So what we want to do next here is have a look at a property of molecules that is a fundamental function of molecular geometry. And that's what we refer to as molecular polarity. You've probably heard that word polarity before. You've heard certainly of like magnetic poles, like the North Pole and the South Pole. In chemistry, we refer to polarity as a property which results from a separation of electric charge due to the unequal sharing of electrons between 2 bonding atoms. Now, what reason would we expect to see an unequal sharing between electrons between 2 bonding atoms? If you think about it, guys, from our previous units, we discussed the ability of atoms to attract electrons to themselves as part of a bond as being referred to as the atom's electronegativities. So essentially, a polarity will result if you have a difference in electronegativities between 2 atoms that share a bonded pair of electrons. That is, the more electronegative atom will pull more of those electrons towards itself due to its greater electronegativity, thereby resulting in a separation of electric charge. That separation of charge leads to the formation of what we refer to as an electric dipole. That is, a separation of positive and negative charge. Now, because it's not fully moving the electrons from one side to the other, we refer to it as a partial charge, and we symbolize that partial charge with a little Greek letter here. That's a lowercase delta here. We call it either delta positive for the partially positive portion of the molecule, and delta negative for the partially negative portion of the molecule that results from the electric dipole. An example that we might see of a polar molecule that I'm sure you've all remembered from back in your biology days is water. So water, I'm sure you remember from back in biology, is what we refer to as a polar molecule. and that polarity of water leads to a large number of its kind of unique properties, in particular its ability to dissolve a large number of other very polar or ionic compounds. And it also has to do with its very, very high specific heat, its relatively high melting points and boiling points for molecules of its size. All of those things result fundamentally from water's polarity. And what we want to be able to do here is to take a look at the geometry of that water molecule and use that to explain why, in fact, that water molecule actually is polar. So let's have a look here and describe its geometry. So to start off here, let's look at the Lewis dot structure. For water is H2O. We have a central oxygen atom and 2 hydrogens around the outside. Counting up the number of valence electrons available to distribute here in our molecule, oxygen in group 6 on your periodic table has a total of 6 valence electrons. And each of the hydrogens in the group 1 of the periodic table have 1 electron. There are 2 of those hydrogens, which leads us to a total of 8 electrons we have to distribute here. We're going to go ahead and make single bonds first. So 2 single bonds uses up a total of 4 of those electrons, which leaves us with 4 remaining left to distribute, which happens to be the total number of electrons which we need to complete the octet for the oxygen. So H2O has a very simple Lewis dot structure here that we've got now diagrammed on the board. And if you look at the molecule as I've drawn it, you might jump to the conclusion here that the geometry of that water molecule is linear, as I've drawn it as a straight line with 180 degrees bond angle. However, remember that these molecules are going to be occupying not a 2-dimensional board like I've drawn them, but 3-dimensional space. And as such, in order to understand the actual geometry of a water molecule, we need to count up our electron domains. So looking around the single central oxygen atom here, we'll notice that we have a total of 4 electron domains, 2 of which contain bonded pairs of electrons, and 2 of which contain lone pairs of electrons. And as such, looking at table 10.2 on the back side of your molecular geometry handout, you'll notice that for a molecule with 4 total domains around the central atom, 2 of which contain bonded pairs and 2 of which contain lone pairs, the geometry here is listed as bent geometry. So water molecules exhibit bent geometry. And with those bent water molecules here, we would therefore expect a more accurate description of the shape of that molecule to be kind of like this elbow right here, where the lone pairs of electrons occupy 2 of the 4 positions of the tetrahedral arrangement of the electron domains, but the actual molecule itself, that is where the atoms lie, represents that bent elbow like we've drawn up on the board. So there's our water molecule with bent geometry. Now what I'm going to do next here is I'm going to go ahead and draw the separation of charge using a little arrow here to represent that separation of charge, to represent the dipole. Oxygen on your periodic table is the second most electronegative element on the entire periodic table. And as such, it is significantly more electronegative than hydrogen. Because of that difference in electronegativities, the oxygen is going to pull more of those electrons towards itself, giving that oxygen a partially negative charge. And so in the bond between the oxygen and hydrogen, I'm going to go ahead and draw that separation of charge using an arrow pointing from the hydrogen towards the oxygen. And that's pointing from the positive side towards the more negative side. Now you notice here, guys, that I drew that arrow as fairly long. The length of that arrow that I'm drawing here is a description of essentially how large of a separation of charge I actually have. And the direction of that arrow points from the positive position towards the negative position of that polar bond. Now, as such, that arrow represents something which has both a magnitude and a direction, which means that arrow fundamentally represents a vector quantity. Likewise, I'm going to draw a second vector dipole here, showing the relative difference in electronegativities between the oxygen and hydrogen in the second bond within my molecule. Again, pointing from the positive side towards the negative side. And you'll notice again here that I'm drawing that vector with an arrow of the exact same length, representing the exact same separation of charge as in the first bond, because there's the same difference in electronegativity between the 2 atoms involved in that bond. So I've got two vectors representing the dipoles present within the water molecule. And as many of you know from back in your physics days, when we're adding vector quantities together, the process of adding vectors involves moving them in such a way that they are added together tip to tail. So I'm going to go ahead and move one of those vectors such that it is added from tip to tail with the other one, and draw between them now a resultant vector that is the sum of those individual dipole moments. And you'll notice here that the sum of those dipole moments yields a vector resultant which points directly upwards, that is, towards the oxygen side of the molecule, away from the hydrogens. And as such, the sum of the vector dipole moments here gives me a overall molecular dipole here with a partial negative charge on the oxygen side of the molecules and a partial positive charge on the hydrogen side of those molecules. And as a result, because there's a net vector dipole moment, we say that water itself is a polar molecule. Now let's take a look at another example here and see how it can turn out differently. The next example that we've got here is a molecule of carbon dioxide, that is CO2. Let's go ahead and again draw the Lewis dot structure for CO2. Again, this is one we've seen earlier, so I'm just going to go ahead and skip right to the structure as drawn, where we've got double bonded oxygens to carbon bonds there for a molecule that looks just like this one I've drawn. And looking at my molecular geometry now, you'll notice that around the CO2, as we discussed moments ago, because I only have two electron domains, each of which happen to contain double bonds, the geometry here around that CO2 molecule is linear. That is to say, in this one, there actually is a 180-degree angle between the carbon and oxygens. And now that I've recognized that, in fact, I do, in fact, have a linear molecule, let's go ahead and have a look here at the dipoles that exist within it. So comparing electronegativities between carbon and oxygen, you'll see again that oxygen is more electronegative than carbon, and as such, I'm going to go ahead and draw the dipole pointing from the positive carbon towards the negative oxygen. And then for the second bond, I'm going to draw the exact same dipole, but now pointing in the opposite direction. And with those two vector dipoles now drawn, in order to sum up the vector dipole moments to determine the overall polarity of the molecule, I'm going to add the two dipoles together tip to tail. And you'll notice that when I add them together tip to tail, the sum of those vector dipole moments brings me right back to where I started. That is to say, the vector sum of the addition of those dipoles equals 0. So even though each of those bonds between carbon and oxygen is a highly polar bond, because the sum of those dipole moments within the molecule equals 0, the molecule itself of carbon dioxide is a non-polar molecule. Whereas water, which similarly had two polar bonds present within it, yielded a non-zero sum of those vector dipole moments. Water itself is a highly polar molecule overall. And you can see now that we come kind of to the key big idea here is that in order for a molecule to be polar overall, two criteria have to be met. Number one, within the molecule itself, there must be polar bonds present. That is to say, there must be somewhere within the molecule that there's an unequal separation of charge due to differences in electronegativities between those atoms. So polar bonds are their first requirement. The second requirement is that the arrangement of those polar bonds around the central atom must be asymmetrical, such that when you add the vector dipoles together, the sum does not equal 0. So again, there's your two qualifying criteria for what makes a polar molecule. You need to have polar bonds which are asymmetrically arranged. Let's take a look at one more example here and see if we can make a prediction as to whether or not this molecule is polar or nonpolar. Let's have a look at CH3Cl. This is a molecule called methyl chloride. Looking at CH3Cl, we've got a central carbon atom bonded to 3 hydrogens around the outside, and the chlorine. And as it turns out, with Lewis dot structure here, I'm going to skip through the actual process of drawing the structure, just straight to the final answer here. This is what our Lewis dot structure ends up looking like. So first of all here, guys, take a look and determine the geometry of the molecule. You'll notice here that my geometry of the molecule is tetrahedral, as we have 4 electron domains around the central atom, all of which contain bonded pairs of electrons. With that tetrahedral arrangement of atoms, there are slightly polar carbon to hydrogen bonds around 3 of those positions there. However, the last bond here, the carbon to chlorine bond, is a highly polar bond due to the greater electronegativity of chlorine than carbon. So again, another way of looking at this is I'm going to try and do a little bit of a 3-dimensional drawing right here. We've got our central carbon atom here, and then we've got those 3 hydrogens that are kind of down below here. I'll draw them with a hydrogen right here, and a hydrogen right here. And then up top, I've got the chlorine bonded to the last pair of electrons there. So this is kind of the shape of that molecule in a more attempted 3-dimensional drawing here. And you'll notice here that there's really only one particularly large dipole that exists within the molecule, because the carbon to hydrogen bond is a relatively nonpolar bond. That is to say, the difference in electronegativity between carbon and hydrogen is only 0.35 Pauling units, and as such, each of those little vector dipole moments are going to be very, very, very small, pointing slightly towards the slightly more electronegative carbon. However, the carbon to chlorine bond is a very, very polar bond due to the much larger electronegativity of chlorine than carbon, and as such, when we add all of those vector dipole moments together, tip to tail, we end up with a resultant vector which is not equal to 0, and as a result, we would say that carbon tetrachloride is a polar molecule. That is to say, it has a polar bond present within the molecule, and the arrangement of those bonds is asymmetrical, which yields a net overall vector dipole. So carbon tetrachloride is a polar molecule. Now, the ability to make predictions about the polarity lead us to some interesting discussions about those molecular properties. Looking at water, a particularly polar molecule, because those water molecules are polar, that is to say they have a partially positive side and a partially negative side, those water molecules exhibit some kind of interesting properties, where we've got the partial negative on the oxygen side and partial positive on the hydrogen side. So imagine now that I have not just one water molecule, but in fact that I have a total of 2 water molecules in my system here. If I have those 2 water molecules, they can arrange themselves in such a way that it puts the partial negative charge of the oxygen close to the partial positive charge of some of those hydrogens. And as a result, we might expect to see an attractive force that exists between the oxygen of one water molecule and the hydrogen of another, due to essentially Coulomb's law, that is, Pauli-Abdul rule, opposites attract. Because that dipole is so very strong in water, and because the atoms involved in that dipole, that is oxygen and hydrogen, are so very small, those things can get very, very close together, and by Coulomb's law, that is F equals K Q1 Q2 over R squared, if the magnitude of the charge is fairly large due to that fairly large dipole moment, and the distance separating those particles is fairly small due to their small size, we'd expect to see the force of attraction between water molecules to be a very, very large number. That is to say, it's hard to pull water molecules apart. And water molecules, therefore, do a lot of things which we see them do in our daily lives. Number one, they tend to form droplets sticking together, that is, they're cohesive. Number two, they tend to have a fairly high boiling point for a molecule of their size. If you consider, like, let's say, water versus another similar size molecule, which is a nonpolar molecule, that is methane, CH4, water is a liquid at room temperature and pressure, whereas methane is natural gas. It is very much a gas at room temperature and pressure. And the difference between those two properties, again, results from the fact that water, being highly polar, tends to stick together, that is more cohesive, and therefore it requires more energy to separate apart those water molecules into widely separated molecules in the gas phase. So again, by looking at some of the geometries of these molecules and making predictions about their polarity, we can then use those geometries and polarities to make predictions about the behavior in terms of their chemical and physical properties. And that's the reason why we actually want to know about molecular geometry in the first place. So this concludes our lecture on valence shell electron pair repulsion theory and molecular geometries. Thanks for listening.